In lesson 4.6, we're going to look at finding zeros of a function again, and some of our zeros or roots or solutions are going to be real numbers, and it's possible that they could end up being imaginary numbers as well. And putting them together, we get the set of complex numbers. So just a quick review of complex numbers. Complex numbers are numbers written in the form of a plus bi, where a is a real number and b is an imaginary number, or bi put together is an imaginary number. Okay, so putting these together, a real number and an imaginary number, for example, the number -2 plus 6i. -2 is the real number and 6i is the imaginary number. Put together, we get a complex number. And basically, if we take the set of real numbers and we add the set of imaginary numbers, and these are kind of math symbols where we have like this heavy side of the R, we get the set of complex numbers, and they use that big bold C to represent the set of complex numbers. And again, the real number is A and the imaginary number is BI. So if we think about where we get an imaginary number, and way back, probably Algebra 2, we introduced the set of imaginary numbers, and we know that the square root of -1 is where we get the I from. All right, so if I have a number like the square root of -4, okay, this would be the square root of -1 times the square root of 4. The -1 would become an I. The square root of -1 is an I, and the square root of 4 is 2. So we would write that as 2i. If I take, or if I wanted to find out what I squared is, this would be the square root of -1 times the square root of -1, which is -1. Sorry. The square root of -1 times the square root of -1 is -1. How about I to the third power? I have the square root of -1 times I squared, which we said was -1, which would be -I. And I to the fourth power would be I squared, which is -1, times I squared, which is -1, and I would get a +1. So just kind of writing those over again, I have I is the square root of -1. I squared is -1. I to the third power is -I, and then I to the fourth power is +1. And if I get to I to the fifth power, we just kind of go back up to I. So this is a cycle. So I can find I to any power by just using these 4 powers of I. So if I wanted to find I to the 57th power, what I would have to do is find out how many times 4 would go into 57 and what that remainder would be. So 4 would go into 57, and I'm just going to write this up here. 4 goes into 5, remainder 1, so 4 goes into 17 4 times, and that would be 16, so I would have remainder 1. So with my remainder 1, this is the same thing as I to the first power, which is just I. If I have I to the 82nd power, 4 would go into 82 20 times with remainder 2. So I have a remainder 2 here. So this is the same thing as I squared, which is the same thing as -1. I can do I to the 105th power. How about 105. So I to the 105 power, I just need to know what my remainder is. So if I do I goes into 105 51 times, that would be 104. So my remainder would be 1. So I would have I to the first power, which is just I. And I can do this with any number by dividing the exponent by 4 and looking at the remainder as being what's left over here. All right, so that was just a little bit of a review. Then we have the fundamental theorem of algebra, and this is kind of an important theorem, and notice how we have a couple exclamation points at the end. Fundamental theorem of algebra. So this is a big deal. It says that every polynomial function, f of x, where the n is greater than 1, so I have to have a power of at least x to the first power, and it says that it has at least one complex zero. So another way to say this is any polynomial of degree n has n roots, okay? But we might have to use complex numbers to get those roots. So if I have an x to the 5th power polynomial, my highest degree is 5. That means I can have 5, or I will have 5 roots. Okay, so that means that every polynomial is factorable It is factorable, and it can be reduced down to linear pairs or irreducible quadratics. And I'm going to show you what that really means once we get to that. Okay, so basically what we have, and if you remember back into lesson 4.5, sometimes we had factors like x plus 1, and then that would break down into x squared plus 4, and remember we said that we couldn't factor this. This would be an irreducible quadratic. That means we can't factor it down anymore unless we use complex numbers, okay, or imaginary numbers. So one thing we need to remember is when we were working with complex numbers is conjugate pairs. Okay, conjugate pairs, and if you look at the word pairs, that means two. Anything that has an imaginary value with it comes in twos. So if you see one, that really means there's 2 roots there. So a conjugate pair, if I use an example of something that we can factor, would be like an x squared minus 4. And this is the difference of squares. So I can break this down into x plus 2 and x minus 2. And we would say that these are conjugate pairs. They have the same number and the opposite sign. Same numbers. O-P-P-O-S-I-T-E, signs. All right, so we have the x's and the 2's are the same, but the sign in between them are opposites. All right, next page. Here they're asking us to write the conjugate pairs. So anytime we have just an imaginary number, it's going to be the opposite. So the opposite sign would be negative, same number, negative 5i. Here on part B, we have 4 minus 2i. This is a complex number with a real and an imaginary number. The conjugate pair, or the conjugate, is going to be 4 and 2i, but we change the sign. Negative 5 plus 4i, we keep the negative with the 5, we keep the 4i, and then use the opposite sign. And then again, negative 3i, like we did at the first one, is just the opposite sign in front of the imaginary number. So this would be plus 3i. Now, if we want the conjugate pair of the complex roots, now this is saying we want actually the pair of factors. So when we think of the roots, we think of factors or the zeros. And if I have a 5i, remember the factors are x minus c. And if I subtract this from x, c is the root, I have x minus 5i and x plus 5i. On this one, I would have x minus, and I'm going to write this here in extra parentheses, 4 minus 2i, and then I have x minus, and then I'm changing the sign in front of the imaginary number. So this would be 4 plus 2i. Now I can simplify this to say that if I distribute this negative, I could have x minus 4 plus 2i, and this one would be x minus 4 minus 2i. So these are the conjugate, that's the conjugate pair. All right, so here's another. I have x minus 5, and then this is actually a negative 5, so actually I can write this as x minus negative 5 or x plus 5, and then minus 4i. And then this would be x minus negative 5 or plus 5, and then the opposite sign of this would be plus 4i. Okay. This one would be, and these are factors here, this would be x minus 3i, and then the opposite of that would be x plus 3i. So these are our conjugate pairs here. So we either get, when we're looking to solve for complex roots, we can get no complex roots where we have all real numbers, or we can get one real number and 2 complex roots, or we can get 4 complex roots or 6 complex roots. But anytime we have one complex root, we're going to have another one that's going to pair up with it. So we're never going to have an odd number of complex roots because they come in pairs. So it's going to be even multiples. So looking at the degree, if I have a first degree polynomial, that means I'm going to have at max one root, or I'm going to have exactly one root, and it's going to be a real number. And if we think about our, oh, I'm not going to go there yet. If I have a second degree, I have two roots. I can have two real roots or two complex roots. Okay, I can't have any complex roots here because I only have one. And if I have a complex root, I have to have two of them together. So that's why if it's first degree, my only root is going to be a real root. If I have a third degree, I'm going to have three roots. They can be all real numbers, or I can have one real number and two complex roots. So I can have a real number and a pair of complex. If I have four roots, or fourth degree, four roots, they can be all real. They can be two real and two complex, or we can have four complex. That would be two pairs. Okay, so we can kind of keep going with this if we want. So basically, when the degree is odd, we have to have at least one real root. That's guaranteed. Okay. All right, so down here it says every polynomial function with real coefficients can be uniquely factored over real numbers into a product of linear factors and or irreducible quadratic factors. That's the same thing I had on the other side. Okay, when I use the example, and I'm going to bring that back. When I use this example here, where this would be a real root and this would be an irreducible complex or irreducible quadratic, and here I'm going to get complex roots, imaginary roots. Okay, so I'm always able to get a complex, at least one complex root out of every polynomial. So what that means is, why is this important? Because everything can be factored. Okay, even if we're using complex numbers, everything can be factored. Okay, so in this first example, we have a polynomial of degree 5 whose coefficients are real numbers, and it has the zeros of 1, 5i, and 1 plus I. Now, if I have degree 5, I have to have 5 roots. Okay, so if these are my zeros, they're also roots. Okay, so my zeros are 1, 5i, and its conjugate, so negative 5i, and I have 1 plus I, and its conjugate, which would be 1 minus I. And if I count these, I have 1, 2, 3, 4, 5 roots, and that's what I should have with degree 5. Now I can also write these as factors, and I remember I'm going to take this and do x minus c. So here this factor would be x minus 1, this would be x minus 5i, this would be x plus, minus minus is plus 5i. Now this one, this is where it gets tricky. I'm going to have x minus 1 and I. So this is x minus 1 minus I. And this would be x minus 1 minus minus I. So x minus 1 plus I. And if you can see, the signs in front of the i's need to be opposites. So these are the factors right up here. And what we could do is we could multiply all of these together to find out what the polynomial is that is made up of these roots. All right, so if I start with an x minus 1, where do I want to do this? If I multiply these together, I'm going to have x times x is x squared. X times 5i is 5i, and negative 5i times x is negative 5ix. So I have a positive 5ix and a negative 5ix, and those will cancel. And then I'm left with negative times a positive is negative 25i squared. And we know that I squared is negative 1, so this would be plus 25. All right, so then I need to multiply these together. Okay, so remember, when I multiply conjugates together, the i's are going to go away. And this is how this works. I'm going to take my x's, so here I have x squared. And then I have a minus 1x, x times I, that's plus ix. Now I'm going to have a negative 1x. A negative 1 times a negative 1 is a positive 1. And I'm just kind of lining up my terms here. And a negative 1 times a positive I is a negative I. Times, let's see, what do I have here? Negative 1 times a positive I is a negative I. And then I have a negative I times x is a negative ix. Here's my negative ix. And a negative I times a negative 1 is a positive I. And a negative I times a positive I is a negative I squared. So if I kind of add up what I have all together here, I have an x squared, and then I have a minus 2x. My plus ix and minus ix cancel. My plus I and minus I cancel. I squared is negative 1, but a negative and a negative is actually plus 1. So this right here is plus 1, and I'm adding this to the 1 I have here, so this would be plus 2. All right, so I could keep going here, and I can multiply my x minus 1 to this term right here. So I'm going to have x to the third plus 25x. I'm going to write this over here because I'm going to have a minus x squared, and then a minus 25. So that's this term. And then I can multiply all of these together now. X squared minus 2x plus 2. So I could keep going, and let's try this. I have x to the third times x squared is x to the fifth. X to the third minus 2x is minus 2x to the fourth. X to the third times 2 is plus 2x to the third. Now I multiply with negative x squared. times positive x squared is negative 1x to the fourth. Negative x squared times 2x plus, or a minus and a minus is a plus x to the third. Now it's plus 1x to the third. Negative x squared times 2 is minus 2x squared. Then I'm multiplying with 25x. 25x times x squared is 25x to the third. And then 25x to the times negative 2x, that would be negative 50x squared minus 50x squared. 25x times 2 is plus 50x. And now I'm multiplying by negative 25. So that's negative 25x squared. Negative times a negative is plus 50x. And then negative 25 times 2 is plus, sorry, negative 25 times 2 is minus 50. All right, so if I combine like terms, I'm going to have x to the fifth and then I have negative 3x to the fourth. And then here I have 2, 3 plus 25, so that's plus 28, x to the third. My x squares are all negative. This is 75, this would be 77, so minus 77x squared. And then my x terms, I have plus 100x, and then minus 50. So that's what I would get if I multiplied all those factors together. Or if I start with this, I would end up with these 5 zeros. That was a lot. So in part B, it's asking us to find a polynomial of degree 4 whose coefficients are the real numbers that has the zeros of 1, 1, and negative 4 plus I. So I know I'm finding the polynomial, so I'm going to end up doing this multiplication again. But my factors are x minus 1 and x minus 1, and then x minus negative 4 minus 1. So x minus negative 4 minus 1. And then I have x minus negative 4 plus 1. All right, so the signs here are opposites. If I multiply these two together, I know that I get x squared minus 2x plus 1. Okay, that's a square of a binomial. Now I'm going to do my multiplying with my imaginary numbers, or my complex numbers, I should say. So I'm going to do this again, kind of like long multiplication. This is x squared this would be plus 4x. This would be plus, this is an I. So this is going to be plus xi, but I'm going to have a minus xi over here. Whoops, minus ix, yes. So these are going to cancel. Then I'm going to have plus 4x again, multiplying now by the middle term. Plus 4 times 4 is 16. And then I'm going to have plus 4i here. So this is plus 4i, and this is a minus 4i. So those I terms have to cancel out. And then I'm going to have negative I times positive I would be negative I squared. So we know a negative I squared is negative 1. So this would be plus 1. So really what I have here is x squared plus 8x plus 16 plus 1 is 17. And if I multiply these two now together, I'm still doing lots of distributive property, really is what I'm doing, kind of like foiling with lots of extra steps. So x squared times x squared is x to the 4th, and that's really what we wanted, degree 4. X squared times 8x is plus 8x to the 3rd. X squared times 17 is 17x squared. Then I'm going to negative 2x times x squared. That would be minus 2x to the 3rd. Minus 2x times 8x is minus 16x squared. And negative 2x times 17. 17 times 2 is 34, so that's a minus 34x. And then I move to 1. 1 times x squared is 1x squared. 1 times 8x is plus 8x. And 1 times 17 is plus 17. So I'm going to add my like terms. So this gives me 1x to the 4th. And then I'm going to add my x cubes. That's 8 minus 2, so that's 6. X to the 3rd power. Then I'm going to add my x squares. 17 minus 16 is 1. Plus 1 is plus 2x squared. 34 minus 8 is 26, so that's minus 26x, and then plus 17. And there is my polynomial. And I think I'm going to stop here, and we'll pick up the rest in a day 2 video.